In this tutorial, we will be discussing ionic compounds with representative metals. Compounds can be either molecular or ionic. Molecular compounds are compounds that form from two or more nonmetals. The basic unit of a molecular compound are molecules composed of constituent atoms. Ionic compounds, however, contain one or more cations paired with one or more anions. A cation is a positively charged ion, which means it's lost electrons. A good way to remember this is the first half of the word cat. Cats have paws. Cations are positive. So that's how you know that cations goes with a positive charge. Anions are going to be the negatively charged, which means that they've gained electrons in the process. The basic units that compose of dry ice, a molecular compound of carbon dioxide, are molecules. However, the basic units that compose table salt, an ionic compound, sodium chloride, are formula units. So let's focus on ionic compounds now. When a metal, which has a tendency to lose electrons, remember losing electrons makes it more positive. So that means that's going to be a cation. Combined with a nonmetal, which has a tendency to gain electrons, making one or more electrons transfer from the metal to the nonmetal. So the nonmetal becomes negative, or an anion. So the metal becomes the cation, the nonmetal becomes the anion. One or more electrons transfer from the metal to the nonmetal, creating a positive and negative ions that are then attracted to each other. A compound composed of a metal and a nonmetal is considered ionic. And the basic unit for an ionic compound is a formula unit. Unlike molecular compounds, ionic compounds do not contain individual molecules, but rather cations and anions in an alternating 3D array. So that means it can go on endlessly until you've run out of ions rather than being individual molecules. If we go back up to this picture, all the CO2s are individual, whereas the sodium chloride just keeps going and going and going. Chemists have developed a systematic way to name the compounds. If you learn the naming rules, you can examine the compound's formula and determine its name, and vice versa. Many compounds also have common names. For instance, H2O, the common name is water. That's what we all know it as. But the systematic name is dihydrogen monoxide. Di because there's two hydrogen, and mono because there's one oxygen. But water is so familiar that nobody ever uses dihydrogen monoxide. We just simply call it water. Unfortunately, there's no way to actually know, there's no system to know the names for the familiar ones. You just have to memorize them. So let's look at how to name the ionic compounds. The first step in naming an ionic compound is to identify that you have one. Remember, anytime you have a metal and one or more nonmetals together in a chemical formula, it's safe to assume that's going to be ionic. So here is the squiggly line that separates the metals and nonmetals. Anything from the left is a metal, anything on the right is a nonmetal. So if you have the left side and the right side together, that's how you know you have an ionic compound. Ionic compounds can then be categorized into two types, depending on the metal. If it only forms one type of ion, it's a representative metal. If it forms several different types of ions, so it has like a +1 at one time and a +2 at another, then it's a transition metal. The first type, type 1, contain a metal from invariant charge, which means that once it has a charge, it's going to keep that charge. It's not going to change charges. We can look at the periodic table and determine what those charges are. +1, +2. All of these are considered transition metals. Then +3, We skip this one and then we start going backwards. -3, -2, -1, 0. You will need to memorize this. There is no way around it. You have to memorize what those charges are. The second type of an ionic compound contains a metal with a charge that can differ in different compounds. Such metals are usually found in the transition metals. That's this area here. For instance, here's copper. Sometimes it has a +1, sometimes it has a +2. That's why we have a different set of naming those. Some transition metals such as zinc and silver form cations with the same charge in all the compounds. Zinc is always a +2, silver is always a +1. Some main group elements, such as lead and tin, form more than one type of cation. That's why we put that X over the carbon, because both of those are in the carbon row. Sometimes they form a +2, sometimes they form a +4, and you have to use a systematic name to figure that out. Binary compounds are those that contain only two different elements. The names of the binary ionic compounds contain a metal that forms only one type of ion. Since the metal always has the same for these types of compounds, it needs not be specified in the compound's name. Then the second half is the nonmetal that ends in "ide." For example, the name NaCl consists of the name of the cation, which is sodium, so Na is sodium, followed by the base of the anion, which is chlorine, so chlor is the base of it, and ending in "ide", so chlorine becomes chloride, so it becomes sodium chloride. The base names for various nonmetals are listed here, and their most common charges in ionic compounds. Notice fluorine, chlorine, bromine, and iodine are all -1. If we go back up here, we stated that this row is -2, where oxygen and sulfur is in the -2 row. So if we go back here, oxygen, sulfur is in the -2, and then nitrogen is -3. It lines up with what we wrote on the periodic table earlier. Some ionic compounds contain polyatomic ions. If we break down that term, poly means many. Atomic, if we take off the IC, we have atom. So we have many atom ions, which means that they share a charge. So there's many atoms here that have come together to share a charge. Ions that are themselves composed of a group of atoms with an overall charge. Ionic compounds containing polyatomic ions are named using the same procedure we apply to the other ionic compounds, except that we use the name of the polyatomic ion whenever it occurs. So we don't change the name like we did with the nonmetals. For instance, here from fluorine to fluoride, if something's a polyatomic ion such as sulfate, it's going to say sulfate. It's not going to change. Carbonate, when you write the name of the compound, it's going to remain carbonate. For hydroxide, it's going to remain hydroxide. We're not going to mess with that name. If you look at this list, you'll notice that there's only 2 or 3 ending in "ide". Chances are, if you have something that ends in "ide", it's going to come off the periodic table. There are a few exceptions here, but for the most part, if it ends in "ite", I-T-E, or 8, you know you have a polyatomic ion there, so you should not be looking at the periodic table to find out what that is. Many polyatomic ions are oxyanions, which are anions containing oxygen. When a series of oxyanions contain different numbers of oxygen atoms, they are named systematically according to the number of oxygen atoms in the ion. If there are two ions in a series, the one with more oxygen in a given name ends in 8. So if we look at this one, NO3 versus NO2, 3 is more, so it ends in 8. The other one ends in ite. SO4 versus SO3, 4 is more, so it ends in 8. The other one ends in ite. If there are more than two ions, if there's more than 2 ions in the series, then the prefixes hypo, meaning less than, and per, meaning more than, are used. For instance, we have 1, 2, 3, 4 oxygens here for chlor. If we compare ite and 8, 8 is more. Hypochlorite, hypo because it has less, and then perchlorate is more than 3, so it got per. So ite and 8, 8 got more. Perbromate because it's more than that. Mite for 2. Hypo because it's less than. Alright, so let's name some of these. First, let's figure out what the cation is. We have Be. Be is right here. It's beryllium. Then F2. F is fluorine. You take the first half, the base of the word, which is fluor, and it becomes fluoride. Na2SO4. Notice I have more than 2 capital letters here. That's a dead giveaway for a polyatomic ion. So we want to look at our polyatomic ion list. SO4 is right here. It's sulfate. So I go back here, and I know that SO4 is sulfate. So Na is right here, it's sodium. And then sulfate. NaI, there's only 2 capital letters here, so that means we're looking right on the periodic table. Once again, Na is still sodium. And I is right here, iodine. That becomes iodide. The first half of the word, and ide. Aluminum and bromine. Aluminum is here. Bromine is here. Bromine becomes bromide. I knew it came right off the periodic table because I only have 2 capital letters there. Here I have 3 capital letters, so I need to go back to my polyatomic ion list. So I'm looking in here, and those letters were NO3. NO3 is right here, and it's nitrate. So that becomes, K is for potassium, and NO3 is nitrate. And then finally we have K again, which is potassium, and 1 capital letter of sulfur, which then becomes sulfide. Notice on every single one of these, look at the squiggly line here. We had the first one was on the left of the squiggly line, the second one was on the right of the squiggly line. That's how I know I have an ionic compound. So just a little bit of an overview and some ideas of how these things come into real life. The active ingredient in bleach is sodium hypochlorite. We can break that down by saying sodium is Na. Hypo means less than the normal oxygens. So if we say this is ClO2, that means that this must be ClO. And this destroys color-causing molecules and kills bacteria. Baking soda contains sodium bicarbonate, sodium hydrogen carbonate, which acts as a source of carbon dioxide gas in baking. Calcium carbonate is an active ingredient in an acid such as Tums and Alka-Seltzers. It neutralizes stomach acids. And finally, sodium nitrite is a food additive used to preserve packaged meats such as hams, hot dogs, and bologna. Sodium nitrite inhibits the growth of bacteria, especially those in botulism. So if we look here, there's molecular compounds and ionic. We just discussed ionic compounds with only one type of ion for the metal. We named the metal, and then we name the base of the nonmetal, plus "-ide". Now remember, there's also another characteristic here that if it's a polyatomic ion, you just keep the name, and it's the polyatomic ion. And that is how you name ionic compounds of representative metals.